everyone. My name is I'm a PhD student at Carnegie Mellon University, guided by the amazing Annie Holly sitting over there. Super stoked to be here to present our work on the fusion of video, IMU data, and biomechanical models to enable accurate full-body markerless motion capture. So buckle in both seatbelts, put down the harness, the ride will begin now. So, as many of you know, traditional motion capture is done in a constrained laboratory environment with very specialized equipment that's quite expensive. But when we use this traditional marker-based motion capture approach, we're able to learn a lot of really cool things about the specific kinematics of the body, which allows us to inform a wide array of interventions for many different pathologies. But we'd ideally like to be able to do the same thing and take into the real world where the patients are over long durations, using totally wearable sensors or portable sensors that are very affordable and can even be put on by the subjects themselves. So there's a couple really exciting emerging technologies to accomplish this. So if you're on this side of the kind of field, you might try to use a computer vision approach, where you leverage the fact that cameras, right, in our society are now ubiquitously accessible, and you try to take a bunch of 2D images, do some fun feature detection using either deep learning or statistical mesh, and then learn about the kind of 2D landmarks of the body, and then triangulate all those images to create and reconstruct 3D pose. Now this is really cool. You don't have to wear anything, but you still need a calibrated environment, so that's one of the main drawbacks. You also have the issue of occlusions, so if any of the cameras don't pick up a motion, all of a sudden your accuracy will drop. And you also need to have representative training data, right, because you're still using data-driven methods. And so if you're not representative for your pathology that you're dealing with, or for a particular motion, you might have some issues. On the other side, you can stick sensors in the body and use a kind of more portable wearable sensors approach. So you could use something like IMUs to try to learn about the body. The downside here is it's not, you have to still wear a sensor, so it can still inhibit some motions, but it can go into totally uncalibrated natural environments. The other main challenge here, though, is that because IMUs give you noisy data about the higher order states of the body, the inertial states, the Q dots and Q double dots, you have to use either additional assumptions or additional sensors to try to update the state of your model, make sure you're recalibrating and not having error accumulate over time. So these are both very exciting. Another exciting thing that our lab has done is shown that you can actually fuse these two modalities to accomplish kind of overcoming both the occlusion issues of the videos and the drift issues of the IMUs, but it's at the expense of, it's not as potent and it's not totally portable, and it's also not only using the ubiquitously available cameras. And so what we've done so far, what this has looked like for us, has been taking a bunch of 2D images. You can do the deep learning part, do some triangulation, you can throw the whole statistical mesh at it to try to correct for any errors that you have in your deep learning approach. And then you can take and project the artificial state of the inertial parts of the body, so the Q dots and Q double dots, and try to match that up to the experimental profiles from your IMUs. And this works, it's really cool. The interesting thing though is there's no dynamic constraints on this. So this is only using the data and it's kind of unconstrained. So we wanted to ask the question, okay, well what if we start to add a model and we try to constrain this process to follow physics? Will that benefit this process? Will that add something that will help the fusion? So that was kind of the first question here. And we wanted to say, okay, what does this do to carefully collected experimental data if an expert collect the data itself? But then the next kind of follow-up is, okay, what are the trade-offs between all of these different approaches, and what happens if we try to benchmark them against each other, and what does that trade-off look like when we start to change the quality of the data? So depending on the IMU data you have, if you misplace it slightly, or depending on the key point data, if you're using really fancy learnable triangulation or single view approaches, it's going to change the outcome, and we want to make sure that we're informed on how to actually do markerless motion capture the best we can for each situation. So for the first hypothesis, we took time-synchronized IMU, video, and marker-based motion capture data and tested all of our different approaches on that. For the 3D key points from computer vision, we used the cascaded pyramid network, which has very high performance on the COCO data set. And then we just did a very simple least squares triangulation. And then we tested with each of the methods. So our method that we're proposing here is we use video data, IMU data, but this time we have a biomechanical model, and we use a pretty simple one in this instance to try to benchmark it. And what we're doing is we're trying to take the model such that we're lining up the anatomical landmarks from the state of the model and the inertial profiles from the state of the model, so the Q dots and Q double dots of the body segments, to the video data, the key points from video data, and the experimental IMU profiles. Now all this is happening, we're trying to constrain it to follow the model dynamics, right, Z dot. Now because there's that T, that parentheses T in there, right, we have a functional. So it's not a function, it's a functional. Whenever you have a functional, you know you were dealing with a trajectory optimization problem. So now we have to use direct collocation. So the main downside, right, is you're adding a lot of computational complexity to your problem. It's going to take more time. But the plus side is you also get out dynamics and contact forces, so you don't just get out kinematics. And so we tested this first against the unconstrained fusion approach, where we're only doing this with kinematics, and we're doing it in a discrete format at each time point, whereas with the other approach, we have to care about all the time points at once. And then we also test this against a video-only approach, so just using the landmarks from the video, the computer vision side, and then just doing an inverse kinematics approach with that. We also tested that against an IMU-only approach, where we're actually using direct collocation in the model state, because in the literature that was shown to be one of the most promising IMU-only approaches. So what we found on the left, you have the mean per joint angle RMC. On the right is the mean per joint position. And together these give you a full picture of how well we're actually tracking the body. So are we tracking the joint angles properly? And are we actually making sure our model tracks the whole body position correctly? Because if it's off, you're going to have a lot of issues with your kinetics as well. So what we found was the vision-only approach, consistent with prior results, performed kind of not as great as we would like in the angle department, especially when you go down to the ankle. It gets a lot more tricky to track properly, but it tracked the pose of the body really well. On the other hand, the IMU-only approach did pretty well with the angles, about as well as expected again from prior work, but it didn't do as great at tracking the position, so that error accumulation is still an issue. And this is with pretty simple walking on this part. And so what we found though was when you go into fusion, right, what makes fusion really powerful is that it's consistent in both regimes. So it's able to not only track the joint angles, but the position over time. So this is where you're starting to see the benefit of fusing these two modalities. And then when we moved to the constrained fusion, we found that it did confirm our first hypothesis that it did perform better statistically, but clinically speaking, there's not really a huge difference between the two. So this would lead you to suggest, okay, if I'm doing markerless motion capture, I probably would like to use fusion because you can maintain consistency with regards to angles and positions. And maybe adding a biomechanical model is not worth the effort it takes to do direct collocation and all that fun stuff. But that's on this data set. So we would look at, okay, if we start to move and slide around kind of the quality of the IMU and key point data, what happens? Is there a time when adding a model to this fusion is useful? And so to kind of simulate this, we've looked at a range of, right, what are realistic IMU noise backgrounds, what are realistic key point noise backgrounds, and what does this do to this trade-off? So poorer IMU data, that's still collected reasonably well, would have some miscalibrations, right? And maybe you have greater soft tissue motion. And then good IMU data would look like, okay, we know exactly when the IMUs are on the body, on the model at the same time, and there's very little soft tissue motion to worry about. Some poorer key point data might look like, okay, I'm using single view methods to extract 3D information, and some great key points would be, okay, I have multi-view methods, and I'm doing some fancy triangulation that's going to learn the intrinsics of the camera, maybe using deep learning. And so when we looked at each of these regimes, what we found was quite interesting. So if you're in the upper left quadrant, you have great key points and maybe poor IMUs, all of a sudden, adding the model is more helpful. So the purple, the constrained fusion, becomes more advantageous when you have this type of condition. On the other hand, if you're in the other quadrant, all of a sudden, adding the model is actually detrimental. Why is this happening? Well, if you think about what the model information is providing to this process, you're actually mainly constraining, again, the Q dots and Q double dots. And that's very similar information to what the IMU data is providing. So when you're tracking IMU data, if the IMU data is already really good, it's kind of redundant to add this extra physics information and to constrain the Q dots and Q double dots to follow that. And furthermore, if you're using a not so amazing model, right, a simple model, and not something that's like fully articulated and very robust, all of a sudden it can actually hurt your results because the assumptions from the model are adding more uncertainty than the IMU data itself. So this is kind of the cool thing. In the other two quadrants, it followed what we saw before, where there are marginal differences that maybe aren't clinically super relevant. So what does this all mean? Well, there's a few key takeaways. First of all, the reason why fusion is cool is because it's consistent across both the angles and position over the single modality approaches. So it helps you reduce both of those challenges. And then the second takeaway is, if you're thinking about whether to add a biomechanical model into this pot as you're fusing everything together, it is recommended, especially when the IMU data is inaccurate. So that's the time when it is recommended. Otherwise, maybe it's not worth it, and maybe you don't need to add that extra computational cost. What does this look like for real collections? Well, poor IMU data in our kind of paradigm we're showing here looks like 5 centimeter misplacements, 10 degree misalignment, and soft tissue motion on the higher end of what happens for the low BMI. So this is still fairly reasonable, and it definitely will happen, especially if you are designing a study where you have a subject that's going to place IMUs on themselves. Yeah. So in those types of instances, if that's something you're trying to pursue, then maybe you should prepare yourself to have to use a biomechanical model. It might help glue things together if you're going to depend on IMU data that might not be as great. So, impact of this work, now there's some initial guidelines for how to go about preparing yourself for markerless motion capture and making sure you're using the best approach for each application. And the main kind of limitation though is we did not benchmark this on every single type of pathology or motion or body type that's out there. So there's still a lot of benchmarking and a lot of nuance. And if you're interested in more of the nuance, there's some more of that in the paper, of course. But if you have a very particular application you're interested in and you want to benchmark these approaches, stay tuned because we will also be releasing a GitHub repository that's hopefully very lightweight, easy to debug, and you can start to play around with some of these different methodologies, the single modality methods and the fusion modalities yourself for your data to find out, okay, when should I specifically use each of these? What is the trade-off going to look like for my application? So you can make sure you're choosing the best markerless motion capture approach every time. So that does it for the talk. Thank you so much for those who made the work possible. A few of them are sitting right there, and excited to take your questions. Thanks for